Okay, so give me 1 second. I'm gonna set my timer so that I don't go overboard. Okay, hello everyone. I am Camila, and today I will be presenting my doctoral thesis defense that is titled 3D Human Pose Estimation from Egocentric Inputs. This thesis was advised by Professor Pablo Arbeláez, and the examination committee is made up by Dr. Ali Tabet, Dr. Kevis Maninis, and Dr. Luis Felipe Giraldo. So let's start off. Give me 1 second because the clicker is not working. I'll fix that right now. Yes, now it is. So let's start off with the overview of what we will cover today on this talk. First off, we are going to talk about an introduction on the topics that we will be discussing. Then I will be talking about 3 of the projects that I worked on during my PhD and how they relate with each other. And finally, we're going to close off with some conclusions. So to start off with the introduction, I want you to picture that we are 5 years ahead in the future, and we have some smart glasses that can help us do something like this. So you want to prepare a meal, and you have a digital assistant that can tell you the ingredients that you have, can tell you the ingredients that you just added. And for example, if you go in and add the salt, it can tell you that the salt was already added. So this type of virtual assistants are the type of things that we want to create through embodied AI. Embodied AI is creating systems that can interact with humans and learn from a physical environment. The way that we do this is that previously most AI approaches used to work solely on the digital space, and now what we want to do is that we want to create a bridge between the digital and the real world. And this can help in numerous applications, like for medical applications, for sports coaching, for example. You can have something like this where they can teach you how to adjust your pose for a tennis swing. And then, as I told you before, you could also have some smart assistant that can help you with daily life tasks. And so moving on to what do we need to create what do we need as sources to create embodied AI? We need to first understand how does our body interact with its surroundings. So how do we do this? We do this first by adding vision to the information that we have. And also we need to have a sense on the pose estimation that we have. So starting off with vision, the information that most computer vision methods have right now is what we would call an exocentric perspective. So as you can see in this video, the way that we're seeing it is from a spectator point of view or a third person, and we are watching someone else do these actions. For example, here, cutting the carrots. However, if I were to tell you to perform the exact same actions that this person is doing, it's probably gonna be harder for you to do it if you only have this information than if you had this one, that is the egocentric perspective. So here what we have is that we have a video in which we are seeing the world from our point of view. And this can help us as people to learn better how to do different movements. We can see now the grasp that the person is having in their hands. And also what we want to reach is for computer vision methods to be able to understand the world from our perspective. So for embodied AI to work, we need to switch from an exocentric perspective to an egocentric perspective. And now moving on to pose estimation, which is going to be the central topic of this talk. So in pose estimation, basically what we are trying to, what the definition that I want to give you is we want to find the full body configuration of a person. And we do this by identifying the joints that each person has. For example, here, this is a drawing and an example of the joints that we would like to have. And we want to know where these joints are located in the 3D space. So there are 2 types of tasks that we are going to be focusing during this talk regarding body pose estimation. The first one is current frame pose estimation, where what I have is that I have information from the past, and I want to predict my entire body configuration for this exact moment. So only where I am right now, and this can be useful in the future for embodied AI applications to learn things like our interactions with the environment. For example, here, if we had a body pose estimation method that could tell us the position of the hands, we could then, with some other processing, analyze that this person right now is holding a knife. and with the other hand, they are holding some vegetables. And then the other tasks that we focused on is called pose forecasting. And here, what we want to do is that we want to predict all the poses that I am going to be having in a near future, given the information that I have from the past. So why would this be useful for embodied AI applications? It can help us identify intended future actions. Like in the first video that I showed you, you saw that when I was going to add the salt, it said that the salt had already been added. That is something that you could achieve if you could predict where your pose is going to be in the future. So for example, here we know that the person is holding a knife and is holding some vegetables. So probably the next action that is going to happen is going to be cutting. And if we had a pose estimation method that can help us understand the movements that are going to happen, then this can help for future approaches. So that is the context on why do we need embodied AI. And now moving on to the problem statement that we identified in this thesis, the state-of-the-art pose estimation methods focus on egocentric perspectives. So there are now good state-of-the-art methods that are able to predict with a fairly good accuracy the pose of a person. However, most of these need a third-person view to work. And when you switch this to an egocentric setting, the methods stop working because there are challenges that are inherent to egocentric perspectives, like occlusions. You have more dynamic environments. There is more motion variability because you're recording with a camera set up in your head or with glasses. And also you can have proprioceptive data, which is the data that tells about our location, and that can be very sparse. We're not going to have that for all of our joints, for example. And so another part of the issue is that there are egocentric methods that have been developed. Now more than ever, there are more methods. However, some of the limitations we also found with these methods are that first, they are trained with very limited real life data. So most of the previous state of the art before we started this thesis, the egocentric methods were trained with synthetic data sets. And what this means is that when we translate it to the real world, it's going to be harder for the methods to generalize. Also, most of the approaches that existed before were assuming that we had a downward looking camera, so a camera that looks directly to our entire body pose. And in practical applications, we are not going to have this. And finally, these methods lack multimodal integration. In particular, the integration that I'm talking about is integrating images or videos with the information of your location. So where my head is at each point in time, which I could have as an input. And so with that, the research question we set up to solve is what novel frameworks can be developed to enable accurate and robust human pose estimation from egocentric inputs, addressing the challenges posed by real-world uncontrolled environments. And to solve this question, I am going to take you through 3 works that we did. The first one on pose estimation through sparse inputs. The second one in which we created an egocentric benchmark to study this task. And the third one in which we used the egocentric benchmark that we created and found what are the limits and where are we in pose estimation. So let's start off with the first one, which is pose estimation from sparse inputs. And here, let's say we have something like a VR headset and some controllers, which are information that we have right now, which are devices that we have right now available in the public. And with this type of controllers and headsets, we could have the information of where our head and our hands are located in the 3D space at each point in time. However, if we want to enable interactive applications, we also need to know how can we estimate the full body pose with only the full body pose of the person by only having as input the head and the hands. This question is what we set up to solve in the first project that I'll talk about, which is called Body Fusion, diffusing sparse observation for full body human motion synthesis. This work was done in collaboration with the Normandy University in France and with Meta AI in Zurich. And it was presented at the Computer Vision for the Metaverse workshop at ICB in 2023. So, to start off, talking about this project, I would first like to give you a short introduction of what DDPMs are, or denoising diffusion probabilistic models. And basically, these are networks that are based, these are algorithms that are based on two processes. So first we would have a forward process in which we start off, for example, here with an image of a dog, and we are gradually adding Gaussian noise to get to this part where we have a completely noise output. And why would we want to do this? Because we're interested in the opposite way. So first we are adding noise, and we know how much noise we are adding each time. Then we are going to go to the reverse process, in which we are going to start off with a noisy input, as you can see here, and then we are going to be denoising it through a denoising function to get to a image output. So the denoising function that we have here, as you can imagine, going from something that is completely full of noise to something that doesn't have, is not a trivial problem. And then the way we do it is by training neural networks that can help us go from one to the other. Why would this be useful? Because then when you have these neural networks trained, what you can do is that you learn how to map target distributions. So these neural networks are able to go from noise to a distribution of pixels that resemble the images that you had in the beginning. So for example, here, we're going to go from noise to a distribution of pixels that are going to resemble dogs. But that is not necessarily the case for all of the approaches that you could do with DDPMs. So specifically for our case, for body fusion, we are not going to be generating images like I showed you here, but we are going to be generating the parameters of a body model. And I want to stop here for a bit and explain more about the body model that we're using. So we are using a simple parametric model. That's the name that they came up for their model. And basically how it works is that you input to a model some relative joint rotations that are going to tell you, so the relative joint of how one joint moves is with respect to their parent. And you also need information of the global root position, because with relative joint rotations, you are able to know the configuration of how my body is being, how am I standing up, whether I'm sitting down, how am I moving all my joints. But the global root position tells us where are we located in the 3D space. And what we do is that we pass this through a parametric model, and we end up with something like you can see here that tells us the position that you have, but it also tells us the shape of the person. For this project, we use fixed shape parameters because we wanted to focus on finding the correct 3D positions of a person. And so with this information, the reverse process that I was showing you before, in which we created dogs, now we're not going to do that, but we're going to start off with really noisy parameters that are going to create these non-human-like poses. And then slowly we are going to be using a neural network to iteratively denoise this input and obtain something like you can see here, which would be a plausible motion. So right now, by using diffusion models, we are able to go from noise to a plausible sequence of motions. However, as you can see here, we are still not adding the conditions. So right now, this motion is not constrained on the hands and the head locations. And how do we add these constraints is the next part that I want to talk about. So we are going to start off, as I already explained, with the noisy input. And we are also going to have a conditioning input in which we have the information for past frames for the head and the hand locations. And our end goal is to find the relative joint rotations and the global positions. How do we do this? So we are first going to condition the sparse tracking signals through a conditioning embedding, and we are going to concatenate this with the noisy input to then pass it through a denoising function. In this case, the denoising function that we're using is DIT, and some things to highlight here is that the reason that we use DIT at that time, using DIT was different from what previous state-of-the-art methods were doing, because they were using UNet, but we wanted to use a diffusion model that was based on transformers, because it is shown on the literature that transformers can help model temporal sequences better. And after we have our joint rotations and global positions, we're going to pass them through our body model and obtain the sequence. So this sequence will already be constrained by the information that we have from the sparse tracking signals. And now moving on to the experimental framework, we use as dataset AMAS, which is a dataset composed by 15 other motion capture datasets, in which they have the 3D body models for different types of actions, as you can see on this image. And for the evaluation, we set up to do 4 different groups of metrics that can help us understand the problem in a more comprehensive way. So first we have the metrics that are related to position, in which we have the mean per joint position error, and we are comparing the position that I have right now, so all the 3D joints that I predicted, versus a ground truth pose. We also have this information of the positional error for the hands, and also for the upper body and the lower body. As you can expect, since we only have information for conditioning in the upper body, our lower body errors are going to be higher, but that's something that I'll cover when we get to the results. We also evaluate how we're doing in terms of rotations, because rotations are the direct output of our method. So we want to see if our relative rotations are the ones that we should be predicting according to the ground truth. And we also devised a set of temporal metrics in which we are estimating the velocity error and also the jitter. These are going to help us understand how smooth our sequences are. And then we also have a metric called foot contact accuracy, which helps us understand more of how our body is, if the predictions that we have make sense in terms of what the body can do. So what foot contact accuracy is doing is estimating if our predictions are actually lifting their feet when they walk, or if they are sliding the feet. And here you can see a table with our results. What I want to highlight here is that you're gonna see the metrics grouped by the 4 classes that I just told you. And also the blue ones, lower is better because these are errors, while the foot contact accuracy is an accuracy, so higher is better. And here are the previous state-of-the-art approaches that were available at the time of creating body fusion. The best one is Avatar Poser. And something to highlight is that Avatar Poser is not a method based on diffusion models, and their network was 30% smaller than ours. So we also set up to create an Avatar Poser large version, which has the same number of parameters as our approach, so that we can make a comparison that is fair in terms of the model size. And here, what we can see when we include body fusion is that we outperform all of the previous state-of-the-art approaches in all of the metrics. In particular, I want to highlight this one, which is the lower positional error, in which, as you can see, we are able to increase this. So this is measured in centimeters. So we are able to decrease the error by 1 centimeter in the lower body pose. And also in terms of velocity, when we have the large version of Avatar Poser, we are significantly better at creating temporally consistent predictions. So now I want to show you some qualitative examples on how does this look. And basically what we have is that we have the ground truth, body fusion, which is our method, and Avatar Poser. The parts that you will see in red are parts that have a higher error in comparison to the ground truth. And you can see that the upper body part is fairly similar for both body fusion and Avatar Poser, but in the lower body part is where we also have some increase in performance. You can also see it here in another pose from the side. You can see it here at the end. And this one I found pretty interesting because even when you're doing poses that are a bit out of distribution from the training data set, so they are harder, our method is able to generate something that is plausible, while Avatar Poser is generating a completely implausible pose because the hand is going straight through the knee, which is something that, well, we couldn't do. Now, moving on to seeing some video examples, you can see here how body fusion is able to maintain temporal consistency. And also this one I found very interesting, which is a zoomed in version of when the method of when our model predicts that the person is sitting down versus standing up. You can see how in Avatar Poser it starts being very shaky. This is another example that shows that we are able to move our feet in a consistent way while Avatar Poser defaults to foot sliding, which was one of the things that I was mentioning before. And this one shows that, like the example that I told you before in the images, even if we don't generate the exact pose that we need to, according to the ground truth, for example, here we are not on our knees, our method is still able to predict something that makes sense and it is consistent with what a person would do. In contrast, Avatar Poser is not generating things that make sense because they are not adapted to this type of generation frameworks. And so the contributions of this first paper that I talked about was that we proposed a full body pose estimation method from sparse inputs using diffusion models. Body fusion, which is our method, uses a novel conditioning scheme that enables smooth motion synthesis, and our model outperforms the state-of-the-art methods. However, after we finished this project, there were some limitations that we identified and that we wanted to explore in the next approaches. So the first ones are related to the method. The first is that DDPMs have a very high computational cost. We are going to be doing these denoising steps that I showed you before iteratively for many iterations. So it's gonna take longer than we would want for a real life application. Also, the method that I showed you doesn't have any visual guidance. The main reason for that was that at the time of creating this project, there were no data sets that included egocentric vision and proprioceptive information of the location of a person. And finally, we have a limited generalization to unconventional poses. Our method is very good at generating poses that are within our distribution space, but when we get conditions that are very far from what we would expect, something like someone standing up, someone doing a handstand, or people that are doing things that are not conventional in the data sets, our method defaults to predicting poses that wouldn't make a lot of sense. So this is something that we wanted to explore further. And then regarding the limitations that we would have by using a body model, first, that it requires data sets with 3D body scans, and obtaining a 3D body scan is very costly, and it's not that feasible to do them for data sets in which you want to explore real life, and people doing activities in real life. And also the joint locations here depend on the pose and the shape parameters. And for example, as I told you before, we have our shape parameters fixed, so we wouldn't be able to, so it's a parameter that we are adding that is not helping us to have the precise joint locations. We argue that it would be better to directly predict the 3D joint locations. And with these limitations in mind, so what I want to tell you about the next project that we created, which is an egocentric benchmark. And I'm gonna drink some water. And so this next project is called EgoExo4D, Understanding Skilled Human Activities from First and Third Person Perspectives. And this is a work directed by Fer at Meta, and it is done in a consortium of more than 13 universities that we were a part of. This was an oral presentation at CVPR in 2024, and I will be giving you an overall introduction of what this project covers, but then I will be also focusing on what were my specific contributions within the project. So the motivation for why we created EgoExo4D was that there are now multiple egocentric vision datasets that are created to study daily life activities. However, first, we have limited structure activities within those datasets. So what do I mean by structure activities? Are groups of activities in which we can find people doing the same type of thing, and we can use them to evaluate different aspects. So this, what you can see here is a word cloud of the different type of activities that are reported in the 5 main egocentric datasets. And what I want you to focus on here is that most of them are related to food. So most of the datasets that we have right now have information regarding cooking, preparing dishes, and different type of things that are not going to give us a lot of variability. And also, there are other datasets like Ego4D, which is a previous version of the one that I'm showing you right now, that has a lot of variability, but these activities are not structured in the sense that each person had the freedom of going and recording their daily life as it is, and it was not divided by takes or different types of information that we would need to train models with specific structure activities. Also, these methods have no multimodal integration. Most of them have video and audio, but they don't have 3D spaces or information of the pose of the person or time synchronized different takes. And finally, we only have one visual perspective. So if you remember in the introduction, I was telling you how important it is to use egocentric vision. But the other part that is also important is that since most methods right now are based on exocentric vision, and it's also part of our world, we need to find a way on how to translate the information that we see in a 3D world to our perspectives. And so we set up to create EgoExo4D, which is the first large-scale data set with egocentric and exocentric perspectives. The videos that you can see here are going to be examples of different activities that we have, and we have time-synchronized takes of egocentric and exocentric views. We collected overall within the entire consortium more than 1,000 hours of videos through 8 structured activities. It includes 740 participants across 13 cities in all the world, and well, we are the city that represents Latin America in the entire data set. And now moving on, and important part of EgoExo4D is multimodality. We use the, let me go back. We use the ARIA devices, which are these glasses, and they come with a rich sensor suite that will allow us to have information from different parts. So we will have point clouds for 3D information. We also have the location of the head, which, as you can already imagine, is going to be an important part that we will use later in our projects. And we also have the 3D views, and we can register these 3D cameras into the point cloud space. Moving on to the scenarios that we have, you can see them here in the videos for some examples. We have 8 structured scenarios across 123 different sites, and our scenarios are focused on skills. So we want to do things that require skill to create, and we have experts in the different type of activities. So we hired, for example, expert dancers, or there were some chefs to do the activities as an expert would do, but we also wanted to have novices in the mix because, for example, for pose estimation, the way that an expert does a specific movement when chopping things is not the same way as a novice, would do it. And we also have our activities are divided into physical and procedural scenarios. The physical ones are the ones that you can see highlighted in blue, are the ones in which what we're caring the most is about the pose of the person and whether the movements that they're doing are the correct ones. While in the procedural activities, the main focus is whether the person is following the right steps to achieve an end goal. Now moving on to the data collection that we specifically did in Los Andes University and the one that I was leading as a student. We collected 4 of the scenarios that I mentioned before. So we collected bouldering, dance, basketball, and cooking. And I want to give you some statistics of the information that we collected. So we overall collected 240 hours of video from the entire data set, and we had 138 participants. This is roughly the 16% of the entire data set. And the part that we were very proud of was that the amount of takes that we collected was 41% of the overall data set, and the takes are the unit that you have for videos throughout the data set. So whenever you're going to use them, you would use a specific take. So even though we collected 16% of the participants and the hours of video, our participants recorded 41% of all of the takes throughout the entire data set. And now talking a little bit about the tasks that we set up to solve in EgoExo4D and the benchmarks that we created, we have 4 of them. The first one is proficiency estimation, where what we have is that we want to, based on egocentric videos, estimate whether the person is an expert or a novice. We also have key step recognition, which is based on identifying the steps that you need to achieve an end goal. We have ego-exo relation, which is relating an exocentric view to an egocentric view, and the one that we will keep talking about, which is human pose estimation. For human pose estimation, we create we at EgoExo4D created different data set annotations. So here you can see an example of how these annotations look in a 2D image. But these annotations were done in 2D and then lifted to 3D. We have 17 body joints, the ones that you could see here, following the MS COCO annotation format. And we are annotating here absolute joint positions. So right now what we're going to have is the position of where my different joints are in the 3D space. This was done through a video annotation at 30 FPS, so we're going to have a lot of information. And to give you a little bit of context of how much information we have here a graph that shows the millions of key points that were annotated versus the different scenarios that we have. And overall, we have more than 100 million annotated key points to work with. We also created baselines in order for people to use our data set and to start working on these problems themselves. And first, I'm going to talk to you about two baselines that were created by other members of the consortium that are also related to EgoPose, and then to the one that I specifically created. The first one is called Ego, and what they do is that they start off with an egocentric video. They predict the head pose estimation, and then they have a second stage in which, with the head pose estimation, they are going to predict the generated motion. The second one is called Poly, and what they do is that they start off with also an egocentric video, and they use a physics-based simulator to obtain the full body pose estimation. And our method, which we named location-based method for this part, starts off with the position and the rotation information of your head or well, the glasses that you're using, in this case, the ARIA glasses, and we're going to pass this through a transformer encoder and an MLP head to obtain 3D full body pose positions. So by using our approach, we were able to obtain the best performing baseline in terms of mean per joint position error as well. You can see here, you can see here the results that we have for the different activities and then also the average. Something that is worth mentioning is that Ego and Poly were not trained on EgoX4D because they are based on using the SMPL body models. Since we don't have body models for EgoX4D because we wanted to prioritize the scale, what they did was that they used their methods for inference, but they were trained on different data sets. And so to close off this section of EgoX4D, our contributions were that we created a data set that provides synchronized egocentric and exocentric views for computer vision tasks. Our data set includes diverse real-world activities in dynamic scenarios, and we devise state-of-the-art baselines to drive progress in 3D human pose estimation. And with all the information that we have so far, we already have a really strong and diverse benchmark. And we wanted to ask ourselves, how can we use the visual information for better pose prediction? If you notice before, our location-based method doesn't have any visual information. That's actually why we named it location-based. And so we wanted to know, if we use visual information for our current frame pose estimation, how much better can it get? And also, since our methods are already performing in a fairly good, we want to know if we can create methods for real-life future pose forecasting. So not only predicting where I am right now at this point, but where I'm going to be a couple of seconds in the future. And these two questions were the ones that we set up to solve in the next part that I will be talking about, which is EgoCast. And it's EgoCast, the paper is titled for EgoCast Forecasting Human Proprioception from Egocentric Data. This was a work done in collaboration with Kevis Maninis and Jordi Fontuset from Google DeepMind in Zurich. And it's going to be presented at WACB in 2025, next year in Arizona. So to talk about EgoCast, let's first define what do we mean by forecasting as a task. So we have as information for our input, past RGB video, and also the trajectory of a person in the 3D space. We are going to get this trajectory by the camera that the person is wearing. So we will have the 3D position and the rotation of this camera from the past. And what we want to do is that, given this information, we want to predict for the future the full body configuration for a couple of seconds in the future for this person. The way that we formulate this task is different from what other people had done previously in the state of the art. First, because we are not assuming that we have ground truth poses as an input at inference. So as you can see here in this orange line, here for the people that are seeing me in the video, in the orange line that we have for the input, we do not have full body poses, because assuming that we are going to be having this is something that is not realistic in terms of how this would work for a real life application. And so what we are going to do is that we're going to predict these body poses. I will explain it in a minute. And then another part that was novel is that most forecasting approaches that exist right now are forecasting up to 1 to 2 seconds in the future and with very sparse sampling frames. So they would be forecasting up to 20 frames in the future. And what we're proposing here is to study whether we can forecast up to 150 frames in the future, which is 5 seconds at 30 FPS. And so how do we do this? We're going to do this by using 2 stages. Our first one is using a current frame estimation method, which would be equivalent to what I was talking about for Ego XO4D. And we're going to do this by combining 2 streams of information. The first one is going to be the positions of the camera. We're going to pass this to a linear embedding and a location encoder. And we're going to have another stream that is going to be the visual stream. This one is going to take as input the images and pass them through a visual encoder. In this case, the visual encoder is based on Ego VLP, which is a egocentric video language pre-training approach. And afterwards, after we have the information from both streams, we are going to concatenate them and pass them through a motion decoder to obtain our full body pose for this specific frame. What we do after we have these predictions is that we are going to use them as an input for our forecasting module. So we are going to pass all of our past information, create our input poses, and then we are going to use our forecasting branch, which is similar to the location branch from the current frame estimation model. The difference is that here we have an adaptive pooling layer to be able to model sequences from different lengths. And at the end, we are going to have a motion decoder that now predicts not only the current position, but the future positions that I will have for as many seconds in the future as I set up to solve. Moving on to the experimental framework, we use the mean per joint position error. And we also created a graph in which in the x-axis, we are going to have the forecasting seconds. And in the y-axis, we are going to have the positional error. And what we want to do here is to calculate the area under the graph. And this is going to give us the information on how good are we performing throughout all of the different forecasting seconds. Since these are errors, the lower that this line is, the better, because it means that you are doing a better performance. And now moving on to the results, we are first going to cover the results of the current frame estimation branch, which is equivalent to the one in Ego XO4D. And for that, I bring back the table that we had before, in which we had the Ego XO4D baselines. If you remember, the location base is the one that I implemented and that only had the location branch. So it would be equivalent to the EgoCast current frame estimation module, only using the location branch. We also tried a part in which we are using only the visual branch, and we can already see that using only visual information achieves better results than using only location information. And then when we do EgoCast full, which is using the visual and the location information, we are able to achieve a 4.1 centimeter of improvement on average for the Ego XO4D dataset. And I want to show you how this looks in qualitative results. So here we would have an example of how these inputs look. So when we're using only the location base, you have something like the input on the left, where the camera is moving towards. And then the information that you would have from an egocentric video is something like what you can see here. And what you're going to see below are 2D reprojections of our 3D predictions. And what I want to highlight here is how when you are not using visual cues, our model is not able to predict, for example, that the hands are moving within a movement. But when you are using the visual cues, I am going to let you see it again. You can see that our hands, that the hands that we predict start moving according to the information. So there you can see it, that it's going forward and then it goes up at some point. So this is showing that the visual cues allows us to have more information on the body pose of the person. This is another example that we found very interesting, and is that when we are not using visual cues, our method defaults to predict that the person is standing. And this makes sense because most of the data sets include people standing. That's the most common pose. But when you are using visual cues, what happens is that the method understands that the person is supposed to be sitting down, and then you get this prediction that resembles sitting down better than when we were not using visual cues. So this is the part for the current frame estimation part, which it gives us the input for forecasting. And now for forecasting, I want to show you our graphs. And here what we can see is that when we go to more forecasting seconds, our error starts to increase. And this is something that would be expected, because the farther that we go, the harder that it is to predict what is going to happen in the future, given the information that I have in the past. We also compared our results against the location-based approach that we had in EgoX4D. We extended to forecasting. And what we can see is that by using EgoCast that uses visual information and location-based, we are able to reduce the error on average by 5.3 centimeters. And this reduction in error is consistent throughout all of the different forecasting seconds. But seeing this, the thing that I found was that at 5 seconds, for example, we are having very high errors. So having something like 40 centimeters of error at 5 seconds is something that wouldn't be feasible for a real life application. So the next part that we wanted to explore was, what are the things that we should be improving and what are the parts that post-forecasting methods should be focusing on? And for that, we created a forecasting oracle, and I'm going to explain that to you here through animations. So we have an input that is our past poses, and we also have a ground truth that is going to be, I don't think you can see the difference in color here, but these ones are yellow and these ones are green. And here what is going to happen is that we have different poses, and we also have a trajectory specified by the ground truth. So it's moving up to a certain way. And what happens is that in our predictions, for example, we could have poses that are similar to the ground truth, but our trajectory is very far off. So we went to the completely opposite side of the room, for example. And what we want to know is whether this is something that is happening in our predictions and if that is important. So what we did was that we translated these predictions to where the ground truths are. And that way we can say, well, what happens if we had the perfect trajectory predictions? And it helps us to identify things like here, where we could see if our poses are actually being correct or not. And here you can see the results that we have with the oracle, which is the trajectory adjusted example that I just showed you for EgoCast. And we can see that the improvement is of 15 centimeters. And this is showing that most of the errors that we are obtaining are related to the trajectories that we are predicting. There are two things that I found interesting here and that I want to highlight. First is the difference between the oracle and EgoCast at lower forecasting seconds versus at higher forecasting seconds. And where we are low, for example, at 1 second, what happens is that our difference is not very high, but when we get further, it starts being very, very steep, the difference. And I hypothesize that this is happening because when you are on shorter forecasting seconds, predicting where you're moving is not actually a task that is going to be way harder, because our method is able to obtain the information that I had from the past and say, well, I'm probably going to be close to where I am right now. Versus when we are something like 5 seconds in the future, our movements are going to be way more far in terms of trajectory to where we were in the beginning. So what this is telling us is that most of the approach that we have is predicting that we are not moving very far from our previous information. And we want to be able to instill into these methods information on how far they can move. And the other part that I found very interesting is this one that I have highlighted here in red, in which after 3 forecasting seconds, the improvement in error doesn't really seem to be, the increase in error doesn't really seem to be very relevant. Let's say it starts to plateau at some point. And what's happening here, I believe that it's because even though we're going farther in trajectories in terms of poses, we are not changing a lot. So the poses that we're doing are going to remain relatively similar within 3 seconds than within 5 seconds. And if you think about it, it would be equivalent to saying, well, if I'm cooking, I am going to go from one space to the other of the kitchen, but my entire body pose is not going to change much from standing up and moving my hands. So this shows that the increase in error from poses is not really going to be that high when you get further. Of course, at the beginning, it's going to increase. And now I want to show you some qualitative results on our forecasting approach. So we would have first the ground truth, in the second row, the 3D pose prediction and the trajectory that we, an aerial view of the trajectory that we have. And you can see that our poses are fairly similar to here, so it's not that easy to discern, but what I want you to focus on here is that even though our poses look similar, our trajectories are the ones that are a bit more far off. So that's part of the same analysis that I was telling you about with the graphs. And here are some videos. The part in red is where what we used as an input, and the rest is what we're predicting. So we're using a short part of previous information, and we can somehow predict the movements. The method, of course, starts degrading the farther that you predict in the future, but this is predicting 4 seconds, and 4 seconds is actually a lot. So it was part of what we wanted to explore. This is another one in which we can see that the trajectory kind of makes sense to what we have in terms of the ground truth. So it shows that our method can predict some trajectories in the right way. And now moving on to the contributions of this last project, we present EgoCast, which is a framework for human pose forecasting from egocentric perspectives. We combine visual and proprioceptive data to eliminate the reliance on ground truth poses at inference. And hopefully EgoCast lays the foundation for advancements in egocentric pose forecasting. And now moving on to the final part of this talk, which are the conclusions. The overall conclusions of my thesis were that we were able to advance egocentric pose estimation in real world scenarios, and we did it through 3 different studies. The first one is body fusion, in which we synthesized realistic and temporally consistent motion from sparse egocentric inputs. Then we also have EgoXO4D, in which we created a data set and a benchmark for egocentric pose estimation in diverse real world conditions. And finally, we have EgoCast, in which we integrated visual and proprioceptive data for reliable pose estimation and forecasting. And overall, throughout the course of this PhD, we were able to establish new benchmarks and hopefully pave the way for practical applications in embodied AI. And now moving on to the future perspectives and the things that I think are exciting for pose estimation coming up in the next couple of months, years, not sure how much time. Some of these things are things that we have already worked on during the projects that I showed you, but I think there's more that could be done, and I wanted to stop a little bit to talk about that. So first, we have adding biomechanics constraints to our pose estimation. So as we know, us humans have actual constraints on how we can move our bodies. So we cannot move our hand up to a certain angle unless it's broken, and well, that wouldn't be useful. And so what we want to do, something that I think would be interesting, is using things like inverse kinematics or adding joint restrictions on how much you can move, or also using the information of foot contact as a loss to avoid foot sliding. Another part that would be interesting, in particular for trajectory estimation, that as we saw is one of the biggest challenges in forecasting, would be to improve our temporal consistency. We could do things like post-processing through trajectory smoothing, or also include additional inputs like velocity or acceleration from the past, because we want our method to be able to use this information and be consistent in terms of velocity and acceleration. Another part that I think is interesting is spatial awareness. So right now we have the benefit that we created with EgoXO4D, which is that we have 3D environments in real time for all of our scenes. So we can actually see how the people that we have are interacting with the environment. I think we could use 3D environments as affordance signals. So for example, if I know that I'm in a kitchen and I have some utensils, I am probably going to focus more on standing up and moving my hands, rather than if I am next to a chair and probably I'm going to be sitting in a chair. So using the information that we have and also using it as restrictions on where our body can be. And finally, we want to be able to create methods that are adaptable to diverse motions and that are generalizable to any type of egocentric input that we find. And right now, by using EgoXO4D, we are advancing into this goal. But I think some other things that we could do for that is, first, there are now more egocentric vision data sets that have been recently released in the past year or so, and we could find a way to join all these data sets to create more generalizable methods. Also, most of these data sets include activity labels and text descriptions, which we could use as additional information for our methods. And that is it for the presentation. This is the list of the 3 main publications that were derived from my thesis that I presented each of these in each of the chapters. And these are the other publications that are related to the PhD, but not to my thesis.